And chapter 6.2 is confidence intervals for the mean when sigma is unknown. So when the population standard deviation is not known, we are using the t-distribution rather than the z-distribution. So if we have sigma, it is the z-distribution in the z-table. If we do not have sigma, if we have the sample standard deviation, then we're using the t-distribution, and we'll use the t-table for that. So we won't be using this formula in this section, but going to introduce it now. This looks exactly the same as finding the z-score when we were dealing with sample means. So it's the same formula, except instead of sigma, we have S. And just a reminder, S is the sample standard deviation. So before we take a look at the t-table, let's go over some properties of this t-distribution. So just like in 6.1 with the z-distribution, we're going to be calling these t-values critical values, and we'll denote them t sub c, and they're going to be on the t-table, which we'll bring up in 1 second. The mean, median, and mode are all equal, and this t-distribution is a graph. It's also going to be bell-shaped and symmetric about the mean. So it's going to look super similar to the normal distribution. However, this is not one set curve. The normal z-distribution is one curve. The t-distribution is technically a family of curves. Each one is determined by essentially the sample size, or more technically the degrees of freedom. The degrees of freedom, which we denote df, is the sample size minus 1. So the shape of the t curve will change based on how many samples or how many data entries are in the data set. And the idea here is that as the sample size increases, the t-distribution will get closer and closer to the standard normal distribution. So if we have, with this little representation down here, if this blue curve right here, so the big blue, light blue one, represents the z-distribution, the standard normal distribution, these other two represent the t-distribution. So this hot pink one is the t when n is close to 30, when there's a sample size close to 30. So the smaller one, the lighter pink one, is the t-distribution when the sample size is less than 30. So you can see that as n gets larger, it is closer to the standard normal curve. Okay, but overall it's a pretty similar bell shape to the normal curve. Okay, let's take a look at this example. Let's read it off, and then we'll take a look at the t-table. So find the critical value t for a 95% confidence level when the sample size is 15. So what we're going to be doing is the similar concept here to what we did before. So we're dealing with the t-distribution, so I'm going to put a t. We are looking for the t-value such that 95% of the area, which is 0.95, falls between negative t and positive t on that t-table. So before, when we were doing it with the z-distribution, we would say 5% of the area has to fall within these two spots combined. So we would say that's 0.025 for 2.5% over here. We would look that up in the table and find the z-score that corresponds to it. It was kind of a pain in the butt. But now when we look at this t-table, so here is the t-table. So the diagram over here on the right, this one is chapter 6 stuff for today, which we'll be doing that in a second. So you can see how it's set up the same way as I just set it up. The stuff down here is going to be chapter 7. Just so we'll come back to that at a later date. So taking a look in this t-table, so we have degrees of freedom. So all of these numbers down here on the left represent the degrees of freedom. So degrees of freedom, we have to remember, equals the sample size minus 1. Okay, and then we also have this level of confidence up here, which is the C value, which is given to us. So we have 80%, we have 90%, 95, 98, and 99%. So that's also chapter 6 stuff. And then the stuff below it, this is chapter 7 stuff. So this is chapter 6 stuff and chapter 7 stuff. So we'll come back to that other stuff at a later date. Okay, so the stuff inside the table now, all of this stuff in here, these represent the critical value T. Okay, so it's a lot easier for this one because all we have to do is look at it and find the T value in here. So before with the Z table, we had to find the area value and then find the Z. All we have to do now is just look in here and that's going to be our T value. So there's actually a very nice shortcut before I actually finish off this problem. We already said that as the sample size gets larger and larger, the T distribution will approach the Z distribution. So if you notice down here that we have infinity, that's essentially saying a sample size of infinity. So when that happens, that would be the Z values, so the critical value Z's. So this last row actually represents the Z values. So this whole last row is the Z values. So there are these hidden critical value Z's on the T table. So previously when we're doing confidence intervals for the Z distribution, we don't have to do it the messy way anymore with using the Z table. We can just go right up here to the top, find that level of confidence, and go right to the bottom, and that's going to be our Z values. Okay, so let's actually do this problem right now. So the problem said, find the critical value for 95% confidence level with a sample size of 15. So for a sample size of 15, in order to find the T value, we need the degrees of freedom, which are n minus 1. So that's 15 minus 1, so that's 14. And we also need to use this confidence level, which was 95%, or 0.95. So from the table, we're going to go to a confidence level of 95%, which is right here. And we're going to go to the degrees of freedom, which is 14, which is right here. And they are going to meet right down here at a value of 2.145. Okay, so that was from the table. So that means for a T distribution with the degrees of freedom equaling 14, 95% of the area under the curve is between negative 2.145 and positive 2.145. Okay, so let's do the confidence interval now. Let's set this up. So for constructing a confidence interval for the population mean when sigma is not known, first we have to verify that the population standard deviation is unknown, the sample is random, and either the population is normal or n, the sample size, is greater than or equal to 30. And then we would have to find these sample statistics. So technically we don't have to be given the standard deviation for the sample here, and we'd have to solve it using that standard deviation formula, but for the most part we're just going to be given it. So we're going to need n, we're going to need s, we're going to need x bar, and then we have to identify the degrees of freedom, which is n minus 1, the confidence level, which is given to us, and then we have to use those to find the critical value t. And then once we're done with that, we have to find the margin of error, just like we did last time. It is equal to that T value times the standard deviation over the square root of the sample size. And then we're going to form this confidence interval. which is the same exact thing as last time. X bar minus E and X bar plus E for the two endpoints. So mu is between those with whatever % confidence that you're given. Okay, so let's do this example here. So you randomly select 16 coffee shops and measure the temperature of the coffee. The mean temperature is 162 degrees Fahrenheit with a sample standard deviation of 15 degrees Fahrenheit. We want to construct a 95% confidence interval for the population mean temperature of the coffee sold. And we're going to assume that the temperatures are normally distributed. Okay, so the first thing that I'm going to put here is that sigma is unknown. We are given a sample standard deviation, that is S. So we are using the t-distribution. We're also told that the temperatures are normally distributed. So those are kind of our two checks here to know that we're doing it in this way. And I'm going to write down some of our givens here. So we have a sample size of 16. We have a sample mean X bar of 162. We have the sample standard deviation of 15. We have the confidence level of 95%. So that's 0.95. So let's find the degrees of freedom now. The degrees of freedom we know is n minus 1, which is 16 minus 1, which is 15. So using these two right here, the confidence level and degrees of freedom, we use the table and find the t-value. So it's going to be 15 and 0.95. So 15 and 0.95, that puts us right here. So we get 2.131. So that's our t-value. And what that means is that if we're on the t-distribution here, that means that 95, because that was the confidence level, 95% of the area for that t-distribution falls between negative 2.131 and positive 2.131. Okay, so that's pretty much the more difficult part here. The rest is just plug and chug. So I'm going to set up what we need, what we're trying to find here. We're trying to find this confidence interval, X bar minus E, so mu is between X bar minus E and X bar plus E. We already have X bar, that's the sample mean. So we need to find E. E is equal to T times S over the square root of N. So that's going to be equal to that 2.131 value times S, which was 15, over the square root of N. N was 16. So we're going to get E is about 7.99. So that's the margin of error. So remember, the margin of error is the difference between the sample mean and the population mean with, in this case, 95% confidence. So now setting up this confidence interval over here, it's going to be X bar minus E, so that's going to be 162 minus 7.99. That's the lower bound. The upper bound is 162 plus 7.99. So for the lower bound, we're going to get 154.01. And the upper bound, we get 169.99. And I'm going to throw a degree sign on here because these have the units of degree Fahrenheit. So there's our confidence interval. So we should label this and we should say that we're 95% confident that the population mean, which was coffee temperatures, lies within this interval. So we had a sample of 16 coffee shops. We measured the temperature of all 16. We calculated the mean of 162. We calculated the standard deviation of that sample, which was 15. and we wanted to construct a confidence interval for the population mean. So we did that and found that the population mean is between 154 degrees and about 170 degrees for all coffee shops. Okay, so pretty similar to what we've already done, except we just have to find that t value just a little bit differently using that t table. Okay, so this one's actually more realistic than using the z-distribution in real life statistics, because we usually don't have the population standard deviation, which forces us to calculate the sample standard deviation and do it this way. Okay, so that is it for this section.